Okay, now I can get to it. So let me go back up here and rewrite this stuff. Let's see, 10. Still didn't change over. Yeah, those are the answers. Huh? No, I can't give it out. I don't have it in here. I'll run you off one. 24 minimum would be 24 volts DC, and the VN max would be equal to 28 volts DC. And then our circuit, like I said, you can draw it like this, whichever one you prefer. And then we'll take our load right here. Our load is going to be equal to 20 volts DC, 5 milliamps through 15 milliamps. And then VN is going to be 24 volts to 28 volts. And then first thing we got to do, right, Matt, is do what? Calculate VRS. So VRS is going to be equal to VRS minimum would be equal to 24 minus 20. So that would give us what? 4 volts. And then VRS maximum would be equal to 28 minus 20. You got the worksheet, Brian? Just do the circuit. Okay, so now we can do the math. And like we said, is that what we're shooting for is we're always wanting current flow through the Zener, right? You understand? So what we're looking for is what causes the current flow to go down. Oh, you got that one right. Yeah, the negative. Yeah. So we looked at over here, we know the current through the Zener follows the input voltage, and that's a pretty important thing to understand, right? So here, when the voltage goes up, the current through the Zener goes up. When the voltage goes down, the current through the Zener goes down. And we're looking for what causes the current through the Zener to do what? Go down, right? So that means the voltage we're going to use, R is equal to V. We're going to use the minimum voltage. Then over here on the current, we know that if load current goes down, Zener current goes up. If load current goes up, Zener current goes down. So that means we're going to use the what? The maximum current. So I'm going to use 15 milliamps, and then we've got a guaranteed current flow. So what we're going to do is we're going to add the IZK. And IZK, so what we did, the only data sheets we have is for the 1N4700 series. So we looked up a watt. Should have looked up a watt, a 20 volt Zener, which was a watt. What's the part number? 1N. Anybody write that down? 47 what? 4747. And it's 250 microamps. We've only got one on Zeners. Yeah. The only one available on Blackboard is for the 1N4700 series. That's the only one available up there. Yeah. So that's a good question. So 24 divided by, open up parentheses, 15 milli, 15 times 10 to the minus 3 plus 250 times 10 to the minus 6 close up my parentheses, equal that. So RS, is this right? Huh? This what? Y'all got to watch out for me. I got other things on my mind. Huh? Yeah, VRS minimum, which is what? 4 volts. So let's redo this. 4 divided by open parentheses 15. I wish you'd have caught me on that before I got through with it. Times 10 to the minus 3, right? Plus 250 times 10 to the minus 6, close parentheses. Yeah, I got to use this one. 4 divided by open parentheses 15 times 10 to the minus 3 plus 250 times 10 to the minus 6, close them up, get that, 262 ohms, right? And we're always going to do what? We're always going to round down for these, right? Always round down, because what we're trying to do is we're trying to make sure that we're moving this current this direction. So we want the I reverse to go up. We don't want it to go down. We don't want it to move toward it. So then what would I do? So I got a 262 ohm resistor. We know there's no such thing as a 262 ohm resistor. So what would I do? Yeah, I would look at the standard resistor chart. And where was that at? It was on Blackboard also, right? On Blackboard, I thought you looked it up while we was doing it in class. Huh? So data sheets, right? Okay. This is it. Huh? This is the one, right? So first of all, we came up here and we wanted a 20 volt Zener. You got your worksheet, Vondell? As soon as it loads. Sometimes Blackboard is so slow, guys. So what would be the next standard size? The ones that look this up? RS. 240 ohms. And then we're using a plus or minus 5%, right? Okay. So what we need to do now is verify that when we go high, this guy right here is not going to go over that. So I'm going to say 240 times 1.05. And what does that give us? 252 ohms, which means this is the right size. Because what we're doing is we're making sure when it's on the high side, it doesn't exceed what? That guy. So this is going to be the perfect size. The 1.05 is a little trick that I showed the last class. So normally in DC, what you learned, would you say, I would take 240 and then I would multiply that times 0.05, and then that would give me a number, and then I would add that number to the resistor and I subtract the number from it. And that's why you come up with a tolerance. But what you find out over time, that if you take any fraction, any percentage, and just put 1 in front of it, and then put the percentage as a fraction, that saved 1 whole step. So that's the same as doing what? Adding 0.05 to that, and then turning it. So let's do this. So let's say 240 times 0.05. What is that? Yeah, 5%. 5%, right? It's what? So now I can take 240 plus 12, and that gives me what? 252. Well, let's take that same number, 240, and let's multiply it by 1.05, and what do we get? 252. So what it does, it saves you 1 step. Right, here you go, Austin. So instead of finding the percentage and then adding it to it, it gives you the direct answer. Now what you can do on the other side is I can take 1, and once you get these numbers in your head, it's going to save you a lot of time. I could take 1, and I could subtract 0.05 from that, which would give me 0.95. So now you got 2 numbers. So to get the low end, I could multiply it by 0.95. To get the high end, I could multiply it by 1.05, and it saves me one math equation, right? 2 math equations. And now you got those 2 numbers in your head. You could have ripped through those things in DC, right? You understand? Because what did y'all have to do in DC? You had to multiply it by 0.05. Then you took that and you added to it, and then you subtracted from it. So 1.05, 1.95. Now you got them. You could rip through those things. But we don't need the 1.9. We don't need the 0.95 because why? Because we're not checking the low side. All we're doing is checking the what? The high side. So it saves you a step in math. In any step that you save, every time you put an equation, you've added another spot where you can do what? Where you can have an error. So you can either do it in your multiplication or you can do it in your addition. Here we have one formula. It don't mean you're right, but it's a less chance of you getting an error. So I learned that a long time ago. So it just saved us a step, right? And what we're doing is we're checking to make sure this is not greater than that. If this is equal to or greater than that, then we round down 1 more, right? You understand that? Okay, so what's the next thing I need to know about my resistor? Yeah, the power rating on the resistor. So instead of trying to go through all these formulas, we know that I'm going to use what? I know the size of the resistor, and I know the maximum voltage it's going to drop. And that's when it's going to dissipate the power. So my power for my series resistor would be equal to what? 8 squared divided by the size, B squared over R, divided by the size we ended up with. So what size we ended up with? 240. So this would give up my wattage rating on the resistor. So what do we come up and get there? What did we get there? 262, 256, 266. Thank you. So what size resistor would I have to use? So these are the standard size. I've got an 1/8 of a watt. 1/8 of a watt is equal to 125 milliwatts. Then the next standard size would be a 1/4 watt, which would be 250 milliwatts. The next size would be a 1 watt. That would be 1 watt. And then we start going in watts. And it goes 2, 5. We would have to use a watt. We'd have to use a 1. Yeah. So we'd have to use a 1 watt resistor. Because it's one of our power formulas. So your power formulas you should know, right? So power formulas, we got three power formulas. We got V times I, and then we got power is equal to I square R, and then we got power is equal to V square over R. And what that does is that saves you a lot. If you know those three power formulas, that saves you a lot of work, right? You understand? Y'all know how they came up with these formulas right here, right? You know how they came up with those? Well, what they did is they just says, okay, Ohm's law says what? Ohm's law says that what? V is equal to I times R. So if they're equal, that means I can substitute anytime I see what? Anytime I see V, I can substitute I times R. So it means I can take this formula right here and I can say P is equal to V, right? I'm sorry, equal to I times R times I. So what I did is I substituted that in there for what? For volts. And that's where that formula came from. So this is your main power formula, but what we're doing is we're taking Ohm's law and substituting it in for each one of these things, right? You understand? And we come up. So what's I equal to in Ohm's law? Okay, V over R. So that means I can take this formula right here and I can say P is equal to V, and that's over 1 times V over R. So that's going to be what? That's going to be equal to V squared over R. So that's where those other formulas came from. They come from the main formula, but what did they do? They substituted what Ohm's law says each one of these values are equal to. So this right here would give me this formula what? Would give me I squared R, and then the other one would give me this formula right here. What do you mean the 8 from? The current flow through the resistor is going to be maximum when the voltage drop across the resistor is maximum, right? You understand? So we calculated up here. We calculated the minimum and maximum voltage drops across the resistor. So what I have is I'm regulated over here. I have 20 volts on this side. Okay. And I can't change colors, guys. I have 20 volts on this side, and over here I'm either going to put what? Over here I'm either going to put 20. I'm going to either put 24 or 28 volts on this side of the resistor. So when is the resistor dropping the most voltage? Well, we calculated. The next thing we do was calculated the minute. So to calculate the resistor, we're not using this voltage and we're not using that voltage. We're using the voltage that the resistor drops, right? You understand? So when is its maximum voltage? Well, when the input voltage was 28 volts, that means we have 20 on the right-hand side of the resistor. We have 28 on the left-hand side, so that means that resistor is dropping 8 volts. So that's when it's going to dissipate the most power, not when it's dropping 4, when it's dropping 8. So what we do is we use the maximum voltage that the resistor would ever drop because that's when it's going to dissipate the most power. Does that make sense where the 8 came from? Yeah. So the 8 came from here, and then the size of the resistor came from the one that we chose, not from the one we calculated, from the one that we chose, right? You understand? So we're going to use a 240 ohm 1 watt resistor right there. And so you have to remember that when you buy resistors, when you look at them, you got to remember that there's 2 things associated. There's actually 3 things, right? What are the 3 things? Ohms, the watts, and then the tolerance. So why don't we use a 1% resistor? Because a 5% works great for these things, right? You understand? So I'd be wasting my money if I did that because it's well within the limit. And what determines how can you tell the wattage rating when you look at a resistor? Its physical size. So that's something y'all need to get used to looking at too. I'll try to find some for you so you can get a physical look at the different sizes these resistors would be depending on their wattage rating. Now, when you get into the big high wattage resistors, it's written on the side. It's literally written on the side. But these little small ones, they're not written on the side, right? So you have to know by the physical size. And that's why when people ask what three things and people say the size, I say, no, it's the ohms. It's the ohm. They're rated in ohms, right? They're not. Okay, are we okay? So what do we need to do now? Now we need to figure out if our 1N47, 1N4747 is going to burn up or not. So we're trying to fit. We know we're going to use this form. We're going to use this formula here. Power is equal to V times I, because we know those two things. I have no idea what the resistance of the Zener is. I have no idea. So that means that's two formulas that scalp the whack for trying to calculate the power of the Zener, because the resistance of the Zener literally changes, right? You understand, dynamically. So what P am I going to use? So the power of my Zener, I'm going to use the voltage drop across the Zener, which is 20 volts. And then times I. What I is going to use? Well, I'm going to use the maximum current that will ever flow through the circuit. And how can I calculate that? Well, I've got a resistor up here, and I've got voltage drops. So I'm calculating the maximum current. So when would the resistor conduct, when would there be the most current flow in the circuit is when that series resistor is dropping the most voltage. Yeah, so I'm going to say 8, and then I'm going to divide that by 240, and that gives me the current flow through the circuit, right? And then what I'm going to do is I'm going to subtract whatever current flows through the here. So I'm not going to subtract here, right? So when my load current goes down, my Zener current goes up. When my load current goes up, Zener current goes down. So what I'm going to do is I'm going to subtract the minimum current, because that's when the current flow through the Zener is going to be maximum. Yeah. So Zener current varies opposite of the load current, but it varies in the same direction as the input voltage. So that's what we're trying to do here, is we're trying to figure out when the current flow through the Zener would be maximum, right? So what did we do here? We calculated the current in the circuit. And then we use this to calculate the current in the Zener. Now, some people like to work this out. So you could, in fact, you can do this with one whack. You can come up here and say what? You can work the formula backwards. So you can say 8 divided by 240 minus, oops, then you can say minus what? Yeah, 0.05 equals, nope, something's going on. Where did 20 come? This is the voltage drop across the Zener, 20 volts, okay? So that's what we're trying to do. We're using the voltage drop across the Zener, and then we're trying to calculate the maximum current that ever flowed through the Zener, right? And I came up with a negative value, which means that can't be right. Eight divided by 240 equals that, right? Minus what? 0.005. Yeah, thank you. Gives me that, right? Then times what? 20. So that's 567 milliwatts. So a 1N4747 will work fine because it's rated at 1 watt. Did I do that right, guys? Anybody get anything different than I got? No, I did. This is 5 milli, which is 0.005. Okay. So 8 divided by 240 gives us 3 milliamps, right? I mean 33 milliamps. And then I'm going to subtract from that 0.005, which would be 5 milliamps, which still is positive. Yeah, mine came up negative the first time because I put 50 milliamps in instead of 5 milliamps. And I multiply that times 20, right? The voltage across the Zener. And then this gives me the wattage rating of the Zener. It gives me the wattage dissipated by the Zener, not the wattage rating, right? That makes sense? So I'm going to make sure that I choose a Zener that, and so on the data sheets, like we went through the other day, all the 4700 series are rated at 1 watt. If I could get these things, if I could get this to pop up, guys, let's see what I got down here so far. Yeah. Me and my network's having a problem. So, okay. Any questions here? Yes, no? Did you show me your worksheet, Vontae? The one you turned in? Huh? No, I need to see it. That's yours. I need to look at it. Okay. So here we have a minus power supply. So my circuit could look like this. And why is the Zener turned the other way? It's minus, right? This guy up here, to calculate my VN minimum, I would take 26 and multiply it by 0.9. Get my VN maximum. I would take 26 and multiply it by 1.1. So where did 0.9 come from? Well, this is the minimum. So where did 0.9 come from? 10%, right? So like I said, now that I have these numbers in my head, it saves you a lot of math, right? So what would 26 times 0.9 be? Well, here I'm using the absolute value, but my answer is going to be in, and then my VN max would be, so what Zener are we going to use? Y'all can see the data sheets. I'm sorry I can't get to them. Oh, so we're looking for a 22 volt Zener. Okay, it's working now, guys. So here's our data sheet. One in, we're looking for a 20 volt Zener. I can get it. It blots out. So one in 4747. This is a Zener. And what else do I need to pick out of this? I need to go over here and look at IZK. What's IZK? Yeah, but the actual one we're for the Zener is 250 microamps. You'll see that? IZK 7447.25 milliamps, which is 250 microamps. Y'all understand? Yes? So we'll need to pick that up later on in our calculations. So what we're going to use, so over here we need to calculate VRS, and we'll just keep it in the same thing. Minimum would be equal to, what's our Zener voltage? Okay. So I'm going to come up here, I'm going to take 23.4 and I'm going to subtract 22. And what does that give me for my minimum voltage across my resistor? What's that? And then my VRS maximum would be equal to 28.6 minus 22. What's that give me? What's that? Yeah, and of course, voltage drops across the resistor are relative to what you're dealing with, right? You understand? Yes or no? So really, there's no negative and there's no positive as far as voltage drops. So it's going to drop 1.4 volts. Huh? That's not negative 22. That's minus. Negative 26. We're subtracting. You can. We're subtracting numbers. So what we're doing is we're using the absolute. Oh, I see. What do you? Huh? So what we're doing is V in maximum, right? Oh, I know what you're talking about. Okay. So what we did is we took over here we calculated the minimum voltage, right? You understand? Down here we calculated the maximum voltage. So what I did is here is this is multiplying it by this is reducing it by 10%, and this is increasing it by 10%. That makes sense? Now, why didn't I use minus over here? Is that what you're saying? Okay. Well, I could have, but you know, I understand your question, but I knew my answers were going to be what? Negative. Does that make sense? So you could take minus 26, multiply it by 0.9, and you would get a minus 23.4. But what I did is I knew my answers were going to be minus. So I just didn't put the sign over there, but that's a good point. Any more? So that answers your question, Brian? Okay. And these over here are not signed, right? Because that's a voltage drop. Are we okay? So what I need, oh, the 22 is the voltage drop across the zener. So this resistor is going to drop the difference between what I put up here and this right here. This right here is fairly constant. So what we did is we took the maximum voltage that could ever be here, which is 28.6, and then we took the minimum, which would be 23.4. So we took the two minimums and the maximums, and what we figured out is, but this side is always going to be what? 22, because it's regulated. Now notice our input voltage always has to be greater than our regulated voltage. Y'all understand why? Because the regulator's got to regulate, right? You understand? And it can't regulate so what we're doing is we're regulating below the variation. So that means the output of the zener would be constant. That makes sense? Yeah. So what we're saying is that this input voltage over here is varying between what? 28 volts, 0.6 volts. It'd be on the bottom side. And down here, this would be 23.4. Well, what we're doing is we're regulating down here. So that means I'm cutting off the garbage that's changing, right? You understand? And I get a good regulated voltage, which is so this is why you always have to regulate below what your regulated variation is going to be at. You have to regulate below that. Because if we try to put our regulator up in here, then what's going to happen is it's going to do what? The output is going to see these dips and stuff in there. Any more questions? So what we're trying to do is we're trying to figure out what resistor I want to use, right? You understand? So what we're going to do, we know we're going to always try to make zener current go away from the knee, right? You understand that? So this is why to get these formulas, to understand the formulas without memorizing them, is we always want the zener current to do what? Move in this direction right here. So we want it to go up. We don't want it to go down, right? You understand that? So what we're going to do is that to guarantee that we have zener current, that means we're going to calculate the resistor. So R is equal to what? Well, I mean, just Ohm's law. R is equal to V over I. So what we're trying to do is figure out what V I want to do, what V I want to use, and what I want to use. So we always want to move it this way, right? You understand? So what we're going to do is we know we're going to use the what? The minimum voltage. I'm sorry. So what are we going to use? Why are we going to use the minimum voltage? Well, that we know if we let the minimum voltage go through the resistor, then if the voltage goes up, zener current's going to go up, right? You understand that? So what we're always trying to do is make the zener current go up. Understand? So this current right here, the input voltage, if the input voltage goes up, zener current goes down. If the input, so it varies. I need to put this some other way. I think I said it wrong. So zener, how do I need to word this? So IZ, so VN, okay. So if VN goes up, right, zener current is going to do what? It's going to go up. And if ZN goes down, zener current's going to go down. So your zener current varies in the same direction as what? As the input voltage. Everybody okay? That makes sense? Yes or no? Now, the load, IZ and the load, So this is ZN. This right here would be ZN. And this right here would be IZ. And this right here would be IZ. Now, I of the load, if I of the load goes down, Zener current goes up. So if the I of the load goes up, then Zener current would go down. So Zener current varies opposite of the load current, but in the same direction of the input voltage. So what we're trying to do is we're trying to guarantee we choose a resistor that always operates above this guy right here, always. So what I'm going to do is when does Zener current go down? So I'm going to use the minimum voltage, right? So if I choose a resistor that'll let that will give me enough current for the minimum voltage, then if the voltage goes up, Zener current goes up, and I'm moving in this direction right here. So we're going to use the minimum voltage across here. So what are we going to use? 1.4. And then I'm going to use the maximum current, right? What's the maximum current? 15 milli. It's given right here. Okay, those two are given. And then what to guarantee, so that would put me right at the knee. I want to guarantee it's going to operate above the knee. So what I'm going to do is I'm going to add IZK to this. And that's 150 micro-rich. So 15 milliamps is going to put it right at the knee. Well, we want to guarantee it always operates above the knee. So what we're going to do is we're going to add the minimum current to operate at the knee. And that's 250 microamps. Now, where did we get that information from? Off the data sheets. So we came down here and used a 4747, and then I followed this over here until I got right there, and that's IZK right there, 0.25 milliamps, which is 250 microamps, right? We okay? So now we guarantee this thing would operate. So even when my load is pulling 15 milliamps, that means I've got 250 microamps flowing through that Zener all the time. Minimum. And that's if we choose we're going to end up with more than that because we're going to take this resistor and always do what with it? We're going to always round it down. So if we round it down, Zener current's going to go up, right? You understand that? So what we're trying to do is we're trying to guarantee operation with all this garbage up in here. So why did we come up with the value of R? What's that? 92? 93.3? Or 93 ohms? Well, last time we calculated 240. Here we're running at a higher current at higher voltages, so that means this guy's going to have to drop, right? It's going to have to let more current flow through. Okay, so what I'll do, and like I said, I can't bring up the standard resistor chart. I think I got sort of a data sheet. In fact, we don't need that, guys. Y'all know where these data sheets are. They're in these green books that we use on test. So y'all can go over and get y'all one. Go ahead. The physical size. So what we're doing now is we're choosing the sizes, and like I said, I'll show you all the different physical sizes when we have time. Well, that's what we're trying to calculate right now. The wattage rating, right? First of all, we've got to figure the resistor. Then we're not going to use a 93.3 ohm resistor. Why? They don't make them, right? And then if it fell right on top of one, So let's say we calculated 100 ohm, we look at our standard chart and we find 100 ohm, we're still going to round down. Why? Because that 100 ohms could have a 5% tolerance. And we're not worried about the low tolerance because the current's going up. We're worried about what makes the current go down, right? You understand that? So we'll always round this down. So inside that data book, there should be what? There should be a chart that gives us the minimum, the standard resistor sizes. So I see 93.3, and what's the closest standard resistor I have to? Going down, not going up. We're never going to round this up. We're always going to go down, right? So what's the next standard resistor size? Below, what's that? 5%, yeah. That's all we're going to use, fellas. What's that? $91 ohm, right? Okay. Yeah, like I said, you can't even get 10% anymore. Okay. So what y'all say, 91, and then I'm gonna multiply that by 1.05. And what does that give me? Okay, because I can't use that one. Why can't I use that one? It's over that. So what's our next standard? 82 times 1.05. It's going to be right because that other one was so close. What do we got here? Which is great, right? So we're going to use an 82 ohm resistor there. Right. Plus IZK. Right. Yeah. You okay? Yeah, let's say, it would be a good idea to get a highlighter and do what? Just highlight these formulas. By the way, this is how much this technology has changed, is that when we first started teaching this course, there was no formula sheet. In AC, too. So everybody see where we got 82 ohms? Yes, no? Are we okay? So now all this garbage is out. We're through. We've chose a resistor now. Now I got to figure out, okay, I got to figure out what wattage rating I'm going to have on this guy. So my wattage rating, I know the voltage, the maximum voltage it's going to drop is what? 6.6. So it's going to be 6.6 squared divided by the size of the resistor that we ended up using. So we're calculating the maximum power that what we're trying to do. We know that resistors are rated in three things. What's the three things resistors are rated in? This will be a good test question, by the way. I'm going to start putting that on every test that I would give. Ohms, watts, and tolerance. Well, we took care of the ohms. We took care of the tolerance, right? Now we're trying to calculate the wattage rating I have to buy for this resistor. Yeah. Well, you tell me the question. When we're talking about what things, so there it is. What things are resistors rated in? Check all that apply. and they're probably going about 10 down there. And one of the answers is going to be size, and one of the answers is going to be size, but that's going to be wrong. Yeah, well, that's what most of the time out of DC, you ask somebody what's it rated in, they'll say size. But size is the physical size of the device, right? So now we can once we learn this, what we'll learn though, what you'll look at is how to associate a size with a wattage rating. So the small resistors, that's what you use to determine the wattage rating. But it's not rated in size; it's rated in watts, right? You understand that? Okay, so what would be my y'all understand the 6.2 squared over 82? Yes or no? Yeah, that's the power formula. And what hopefully what you're seeing is we're taking the formulas you learned in DC and we're learning them how to apply them to these other devices. All you got to do is figure out V squared over R, what you're going to use for V and what you're going to use for R, right? So what's the wattage rating on this resistor got to be? So we got to use at least a 1 watt resistor, right? I think we got some 1 watts over there. I have to go look. In fact, y'all go ahead and take a break, guys. Across the resistor. Not we the resistor is not dependent on what's on this side and what's on that side. It's how much it drops, right? You understand? Yeah. So this, we calculated this right here. Can you see this, Bernard? This is the maximum voltage that resistor would drop in this circuit. So we know we got 22 volts on one side, we got 28.6 on the other, so it's going to drop, the maximum it'll ever drop would be 6.6. And that's when it's going to dissipate the most wattage, right? The size of the resistor that we ended up using. Not what we calculated, what we ended up using. And that's a common mistake people make, is they use what they calculated and not what we ended up using. Yeah. I'm going to pass these around. These are different sizes of resistors. This right here is an eighth of a watt. Can you see it? And then this is a quarter watt. And then this is a half watt. And this is a 1 watt, and this is a 2 watt. And that's about as high as they'll go. Once we get into the higher wattage ratings, a lot of the resistors get really big. And since they're big enough now, instead of using color codes, they just write it on it. So this is a 47 ohm resistor, and it's a 6.5 watt resistor. So the higher the wattage rating, the bigger the physical size of the resistors got to be. So sooner or later they stop using color codes, so they just write it on there. Here you go, Matt. And it goes right up the line, and I think we got it all the way up to a 2 watt in there. So I think that finished up the second circuit, right? I'm sorry, the third circuit. The first circuit we worked in class. Everybody okay there? Okay, so this is circuit number 3. So here I give you the minimum and maximum values. I think I got a color. Yeah, okay. So Vn minimum is going to be equal to 7 volts DC. And Vn max is going to equal to 8 volts DC. So VRS minimum is going to equal to 5.6, that's our Zener, is going to be equal to 7 minus 5.6, and then my Vn max it's going to be equal to 8 minus 5.6. So what we got here? Okay, so we need to look at our data chart and in our this guy and find a 5 point, what is it? 5.6 volt Zener. Just say 5.6 volt. Oh, here it is right there. 4734. And I finally did get it to come up on Blackboard, by the way. So if it shows up a little better. So 5.6 volts would be this guy right here, 4734. And then IZK, we'll go ahead and get that now, is 1 milliamp, right? One in 3734. So draw my circuit. Now this is a positive supply, so the Zener cathode goes toward the positive. And my load will be out here. Over on this end, we're going from 2.6 volts up to 3.6 volts. Over here we got 5.6 volts running between 0 to 100 milliamps. And we end up using a watt of 1 N, 47, what? 33, 34. Okay, so we start off by calculating RS. So RS is equal to the minimum voltage, right? Which is what? 2.6 divided by the maximum current. Yeah, 100 milliamps plus IZK, which is 1 milliamp. And we looked that up in the data sheet, right? So what's the calculated value for RS? Ohms? Yeah, 26. Yeah, we're always rounded down anyway, guys, you know, so the fraction here is useless. Just round it down, right? No, if it's 26, oh, you mean the one we're going to choose? So then what we're going to choose is we're going to choose 24, and then we're going to multiply it by 1.05. What does that come up and give me? 25.6. So this guy's going to be good, right? So we're going to use a 24 ohm resistor for RS. Then I know the ohm value. What's the next thing we need to do? Power. Good. So the power, so this is 1, step 2. This would be step, what, 3? So my power across my resistor is going to be equal to what? V. So what V we're going to use? The maximum it's going to drop, 3.6 squared, right? Divided by the what? Size of the resistor. We chose the what? 24 ohms. So we'd choose at least a 1 watt resistor. Are we okay so far? Now I got to figure out if I'm gonna burn my zener up, right? You understand? So power across my zener would be equal to the voltage on the zener, which is going to be 5.6. Then we're going to calculate the maximum current flow through the circuit. So that's going to be equal to 3.6 volts divided by the series resistor, right? You understand that? So that's going to be 24. And then I'm going to subtract 0 from that because that's the minimum current it'll draw. So this is going to work out. So what's the power in our zener? I think this is going to be dangerous, right? Okay, we squeezed it in. Yeah, because it's a 1 watt zener. We're right under the limits. Yeah, all these zeners are 1 watt zeners, right? That's it. I don't think there's another version. Thing to do is probably just rework these and then verify that you worked them right. So here, this is the next circuit. Are we okay? Okay. What you mean? Go back to this one? Yeah, we can do that. So I'm not going to work this. You read my mind. Great minds think alike, right? Yeah. Huh? Then we'll go over it. Yeah, we'll do that. So I'll leave this one up here, Bernard. But what I'm going to do is I'm going to pause this, give y'all time to actually work. So first of all, we need to calculate VN minimum or maximum, whichever you want to do first. That's going to be equal to 24.4 times 0.9. Then VN maximum is going to be equal to 24.4 times 1.05. What have we got? Minimum 11.16, 11.2. And then VN maximum. Everybody okay? Then we're going to calculate the RS minimum and VRS maximum. So our VRS minimum is going to be equal to 8.2, which is our zener voltage, minus 13.6. Sorry, got that backwards, guys. 13.6. 13.6. Indicated the same answer, but it'd been minus. Minus. No, I'm sorry. The minimum voltage, Rick. The minimum voltage would be 11.2 minus 8.2. What does that give us? And then my maximum voltage would be 13.6 minus 8.2. What would that give us? Okay, our circuit, let's draw it like this time. This is a positive regulator. I'm going to take my output in parallel with the zener. So whatever's across the zener is going to be across the load. VZ is equal to 8.2 volts. My load needs 100 milliamps through 150 milliamps. But my input voltage is going to vary between 11.2 volts through 13.6. And what zener we're going to use? So 1N 4738. Is that okay? And then IZK, what's IZK for this? We might as well go ahead and write it down. 500 milliamp microamps. Yeah, because the maximum we get, yeah. We're okay? So 500 milliamps. Yeah. So next we need to now we're ready to calculate RS, right? So what voltage am I going to use? Huh? Okay, so what's that? 3 divided by what? 150 milli plus 500 micro. Good. So what does this give us? 19.93. Yeah. So we could use we never go up. Never go up. So we can use 19.9. That's okay. But we on Zeners. So this is a little different. On Zeners, we never do what? We never go up. Yeah. Well, it might have still worked out because 19.9 and 20 is okay. So you still had a chance of choosing the right resistor. But if it was 19.5 and we round up, then you might have chose the wrong resistor, right? You understand? So here you probably no big deal. We still can use 18, right? So, well, what I'm saying is that if it was like 8, so you'll probably, that makes sense. So we'll come over here and we're gonna take this and find the next standard size. So we're still working on equal. So what's the standard size closest to this? Down from that. Okay. Always down, right? Then we're gonna multiply this times 1.05, which gives us what? 18.9. What we're trying to do is we're trying to see if this comes up to be greater than that. It's a check. Because what we're doing is we want the Zener current to always go up. The problem is that the resistors we're choosing can be within 5%. So that means if I come up here and I use an 18 ohm resistor and then point 0.5 put it then 5% put it above that, then this circuit might work and the next circuit might not. So the one might regulate and the next circuit might not because it's within 5%, right? You understand? So what would happen is this guy where it was on the high end, it was sitting up here at 18.9, this guy wouldn't work because I didn't compensate for it. So what we're saying is that now, no matter, I can go out and I can just pick up this 18 ohm resistor and we're okay. Whether it's 18.9 or whether it's on the high side or whether it's on the low side. The low side takes care of itself, right? You understand? Because if it's on the low side, that would just cause the inner current to go up a little bit. But if it's on the high side, you could go out of regulation. So we're fine. Good job, guys. So now I've chose a resistor. So now I've got an 18 ohm resistor. So you don't use that anymore. We're through. Once we choose that resistor, that's the resistor we're going to use from now on. Right? Understand? Yeah, that's the problem we have, right? Because we came up with a 19.9, but there's no such thing as a 19.9. And now if I used a 20, it would have definitely went out of regulation, right? You understand that? Because now it's going to be operating. Are we okay? Just makes sense? Okay, so what we're going to do is we're going to choose this guy right there. Now, no matter if I got one that's got a tolerance of, it's actually tolerance is 1% or this tolerance is 5%, it's going to work. Okay, so now next thing we got to do is calculate the power, right? So we're going to come over here for PRS. We don't need that right now. All we need to do, we could use current. You can use current, guys, but I already know enough to calculate the power of the resistor. I know the maximum voltages are dropped, and I know the size of the resistor. And no matter what you do, you're going to come up with the same wattage. You can go ahead and take 5.4. You could divide it by 18. You could come up with a voltage, multiply it by 5.4, and you'd come up and get the same answer. It's whichever one's easiest for you to do. Well, see, that's fine, it's fine. It's fine. So we're going to have to use at least a 2-watt right there, guys. At least. So that would be, and what you got to understand, and why do I want you to show your work? Because if you miss that one, and then you used your answer out of that one and plugged it into all your equations, the other equations, right, you would get credit for, you would miss one, and you'd get all the rest of them right? You understand? Because you showed your work. If you don't show your work, then you miss that first one, then you'd miss all of them. I'm not going to try to figure out. I'm not going to come back. Wrong room. So now we've got our size. Now we've got everything we need to know about that resistor. 18 ohms. We know it don't matter now whether it's 5% high or 5% low. We know that, and now we chose the right wattage rating. Right? Everybody okay? Yeah, but the way it's set up, I'm not asking you for what size. I'm just asking for that answer right there. So I'm not asking you right now to actually choose the wattage rating, but you can see how it goes, right? Okay, guys, what do we need to do now? We need to figure out if we're going to burn up our zener. So power across my zener is going to be equal to 8.2 volts. Then we're going to calculate the maximum current in the circuit. So I'm going to use the maximum current across that voltage across that series resistor, which is 5.4, divided by the size that we end up using, 18. And then I'm going to subtract from that what? The minimum current, right? Yeah, because remember, zener current varies opposite of load current. So if the load current goes down, zener current goes up, right? You understand? And that's why having these ratios in your mind. So you get out there, guys, and you see these dang series resistors burn up, you need to replace it with the exact same size and the exact same wattage rating, right? What's that? So we just burned up our zener. Bad design, right? So what would that mean we would have to do? Yeah, it's the 1 in 4700 series. They're all 1-watt zeners. We talked about it's right on the left in the data sheet. So what does that mean? Well, that means I cannot use I cannot use a 4700 series. So now I'm gonna have to go back and find a zener that would work. So what we did is we chose a zener that we had, right? You understand? Then we realized from the circuit design it wouldn't work. So we'd go back and choose another zener, and you wouldn't. the only thing you might want to look at, all this is probably going to change. All this is probably going to work. It's just that you're going to go up to a 2-watt Zener now, and you wouldn't have to redo any of this math. Everybody okay? Just make sense? Yeah. So we just have to go up to at least a 2-watt Zener. So I would come up and I would just type. I'd go on the internet and I'd just type in, or if I had a part supplier. So we buy a lot of stuff from Jamico, and that's a really good part supplier, by the way. And I would just type in 8.2 volt 1-watt Zener, and it'd pop one up there, and I'd order it. If I was going to use a lot of them, I'd go ahead and order a few because they start reducing the price over time. Oh yeah, Jamico's a really good spot. Oh yeah, I brought the door over here before some of y'all got in. I don't know where it's at. It's out there somewhere. A little plastic door that's got 5 or 6 resistors in it. Yeah. So how do we do? You know, common little mistakes is okay, but what we need to do is always go back and double check your work, right? You understand? I think I told you about. I was in college at Jeff State, and I took an algebra test, and I ripped through that thing. I was the first one to turn it in. I say, Rich, you aced it. And I got it back. Guess what I made on it? I know I didn't make 0. I made 70. I made a 70 on it. And then when we went over in class, guess what it was? It's just common mistakes, just mistakes. So after that, if the instructor gave us 2 hours to take a test, I took 2 hours. And I aced every test after that because I went back and did what? Yeah. In fact, the guy decided, wanted me to change my major to math. No way. No way. Okay, so let me run this off and we'll start working on this in class and we can let y'all converse with each other. So we're going to have a lab on Zeners. You'll see it? Here we go. And I'm going to go print this off, and what we're going to let y'all do is we're going to actually figure out the design, and then we're going to wire this puppy up. That's a good question. Let's go back and look. So here's Blackboard. So we have finished up, we just finished up the lecture on Zeners, right? Y'all understand that? So when I go into course content, and then I look at Zener diodes, and then there's no topic quiz. There should be one in there. Let's see if there's one in there. There should be, guys. I need to do that. I thought there was one. Well, what's nice about topic quizzes is that they give you a pretty good idea of what's going to be on the test. So I need to go back and add topic quizzes here. So here's introductory. So here we have no topic quizzes. Yeah, so I need to go back and add that to this course. I really do.